It's time to get high with a dose of math. In the previous video, I've explained the Euclidean algorithm. It calculates the greatest common divisor. In this video, I'll explain the extended Euclidean algorithm. To define what it does, I have to put some algebra here. Given integers a and b, the extended Euclidean algorithm finds a set of integer solutions for c and d for this equation. The GCD of a and b equals to ac plus bd. Given a and b, find c and d. If you are familiar with the modular function, it is similar to finding the modular inverse. So you might want to take some time to digest this problem. We will use the numbers in the previous video. So the question is, 73, the GCD, is how many times 45333 plus how many times 10,001. So the big idea of this algorithm is that we express the GCD in terms of the dividend and the divisor of the same line. Starting from the bottom and moving upwards by substituting the remainder. So in this bottommost line, we start with 73 equals to 0 times 657 plus 1 times 73. And now the next line, 73 equals to how many times 4672 plus how many times 5657. So let's write in the margins. So we use the equation of the same line in the generated by the Euclidean algorithm. We first express 73 in terms of 657 and 4672. So 73 equals to 1 times 4672 plus negative 7 times 657. Negative because you brought this term over. So to make things simple, if you want to add, you want to subtract a number, it's better to add as express it as adding a negative number. So I did it this way. Now we need to do some manipulation, which is quite a bit confusing, so it will help that if you have done such an algorithm by hand before. I'm just teaching how to implement this using as an algorithm. So since this is an algorithm, you have to express the next line, which is the second line, in terms of the previous line. So we can deduce that the number of 4672 is equal to the number of 73. This is because there's only one copy of 4672 in the expression of 73. Okay, good. Now the more challenging part. How many 657s are there? You have to take into account the ones from the substitution and the ones carried over from the previous line. So from the previous line, there's 0 657s. Okay. On the other hand, from the substitution, there's 173, and in the expression of 73, there's negative 7 657. So finally, the number of 657s is equal to 0 657 carryover plus 1 times negative 7 657. Negative because you brought this term over and you express it, and then you get a negative number here, so negative. Okay, looks like we reproduce the same line, but although it looks the same, but it is actually different because we express it in terms of the previous line. So to show that this really works, we produce the next line. So in the margins again, we express 657 in terms of previous two remainders. So doing it the same way we've done before, 657 goes to 1 times 5329 plus minus 1 times 4672, minus 1 because you brought this term over. So once again negative because, yeah, okay. So we substitute 657 into the second line to generate the next line. So since we have done this before, so we can just copy and paste the functions. And there you go. To confirm that this is true, we already have the left hand side, which should be the GCD. to be equal to the right hand side. So what we've done again is to express the GCD in terms of the next two remainders. So since we are doing the same thing over and over again, so let's copy and paste, and magic, the solution is here. This is C and this is D, answering the question. So you might feel that solution came out too quickly, but I have already explained it how the next line is deduced, and if you are correct by induction, you should get that. So anyway, here's an idea of how it works. The keyword is substitution. We express each of the remainder in terms of the previous two remainders. Then we continually substitute each of these remainder into the line to generate the next line. The result is the GCD expressed in terms of the first two remainders, which are A and B themselves. So here's hope you get the idea. Here's something to note. There are infinitely many sets of integer solutions to the equation. So you can add 45333 times 10,001 to this side and subtract the same amount from the other side, and you get another solution. Balance the equation again and you get yet another solution. So you can try that out yourself. We will now move on to another set of numbers to show that this algorithm works in general. So let's clear this scribbling first, and using the numbers that you're familiar. There. So there's enough lines. Let's copy and paste. No, 65537, not 655. There. And now we move the bottom line of the extended Euclidean algorithm down, and we fill up the middle. There we go. The solution confirmed. Once again, you can download this file and try out numbers for yourself. Signing off, this is a dose of math.